So welcome to Machines and Models. That's Unit 1 of COMP526, where we'll talk about the basic mathematical abstractions that we'll use for our algorithms. The learning outcomes are stated here. Just to briefly summarize this, we'll talk about analyzing algorithms. So when the last unit was a bit about proving to ourselves and others that an algorithm does the correct thing, then this unit is more about, does it do it fast? Because there are many problems where getting the answer in some unspecified time is as useless as never getting it. We'll talk about the random access machine model and the big O classes. And we'll check on a few examples how we apply this. There will be more examples in the later units for specific topics and algorithms. It's an algorithms class, but I haven't really defined algorithms so far. So at least in week 2, we should do that. I'll go basically by just a simple intuitive explanation. Algorithm is a sequence of instructions. And you can think of that as similar to a cooking recipe. But there's a few points where the analogy is a little breaking down or needs a bit more of clarification. First of all, as anyone might have noticed, if you get passed down some recipes from your mom, it's sometimes not clear what one step really means. And we don't want that for algorithms. Everything has to be so clearly defined that a stupid computer can execute it. We also insist that the program that's making up an algorithm is finite. So you can't have, oh, now let's distinguish all possible cases, and I'll just list them all. If there's infinitely many of them, that doesn't count as an algorithm, because you could never finish writing it down. You could never feed such a program to a computer. Now, what I've said so far is basically just telling you what a program is. An algorithm, on top of that, should be a solution to a general problem. So instead of just computing some specific example, it should work for a whole class of problem instances. If you want, think of it as not adding two specific numbers, 17 and 4, but being given two numbers without knowing in advance what that number will be, you can add them up with your algorithm. That's the distinction. It's a little, wow, if you look at it too closely, it's maybe not so clear what this means. You can formalize this further, but I don't think it has benefits for us. The algorithms in our module will always have this input-output abstraction. So you get certain things as an input, then your algorithm does things with them and produces an output at the end. If you want a more typical example, apart from just adding two numbers, you can take a sorting algorithm. For example, bubble sort is maybe the simplest and most well-known because it has a funny name and at least it's easy to specify. Another thing here that I want to make clear, the distinction between an algorithm and a program can sometimes be a bit fuzzy, but what we think of as an algorithm is usually a core idea that makes up how the thing works. Like in bubble sort, this bubble operation means you look at two consecutive things, and if they're out of order, you swap them. And then you basically say, cook until done. Repeat this until nothing more happens. Or you can say it a little more precisely. Go from left to right and continue doing that until nothing ever changes anymore. And there's twists to that, all of which we would say that's still bubble sort, but there could be 5 different programs that all look slightly differently in the details. But we want algorithms to mean something slightly more abstract. Again, this is an idea that's hard to grasp because it would mean to define what is abstract enough. I think in the examples that we talk about, you will usually have no problem distinguishing a concrete program from the algorithm, or from the algorithmic idea. We'll mostly talk about algorithms, but we'll also talk about data structures. So what's the data structure? Question? Pardon? Speak up. Okay, there, I will put them up after class. Yeah, apologies. I think I promised to put the slides up in advance. I think I just forgot for this. I didn't make any last-minute changes. Could have just uploaded them. Yeah. Yes, you can always look at last iteration. There's a few changes here and there, but many bits are the same. So what's the data structure? This is a bit more than an algorithm. We also have a notion of state, and we have a notion of some things that are kept over time. So in an abstract sense, it's a rule for encoding data, and the data structure specification will have to tell you what data means. So it's a way to encode something in computer memory, in binary at the end of the day. Plus, it's a set of algorithms to work with the data, either query it, ask questions about it, or modify it, update operations. If you've seen a data structures class or algorithms class undergrad, then you would have seen a binary search tree, I hope. That's one standard example, and we'll cover more. So the unit 2 will be a basic recap of some of these data structures that many of you will have seen, but we'll recap them quickly so that everyone's on the same page. Okay. Now that we've set the term straight, we can start with the real bit of this unit. In the next subsection, we'll talk about algorithm analysis. So again, getting at how fast is an algorithm, as opposed to just does it get the right answer at some eventual point in time. So why do we do this? Often when we have some algorithmic problem, there are different ways to approach it, and we would like to find a good algorithm for it. And if there are several, we want to compare them. Now, what good means depends on the application, but most of the time it's being fast. So finishing the job earlier is usually our main criterion. And sometimes space is a concern as well. Space often has this weird behavior. If you have enough, it doesn't matter. But if you're out of space, you're completely screwed. And so it's a bit of a threshold thing. If you can expect an algorithm to take too much space, you have to worry about it. If you expect it to be fine, then time is the main criterion. I already said we want to compare different algorithms. There's a second goal of algorithm analysis, and that's, if you think from an engineering perspective, to predict how long something takes in a concrete application. We'd like to be able to do that so that you can estimate if some approach that you have in mind is viable or not. It's a very basic thing that engineers do all the time. I guess in programming and computer science, it's a little less needed than elsewhere because we can iterate faster. Often it's enough to just build it and check it. But there are cases where this is not good enough. If you plan a big enough system or plan an entire architecture, you have to know roughly how long will things take, or is the resource consumption within the boundaries of what's doable. It can also become a cost question. Everything's moving to the cloud, so computation often means dollars at the end of the month on your AWS bill. So it's definitely relevant to make a proper prediction of that. One obvious way to do a comparison of algorithms is implement it and run it. As I just said already, it has a few shortcomings that in various ways can be a problem. You have to know relatively well what you're going to do at the end with your algorithm or with your implementation. Otherwise, you can't get proper test data. That could be a real problem. If you're building a service that gets data from a client, you don't necessarily know what's coming. So all the results you find with running time experiments or running time studies are valid for the machine you tested it on, are valid for the concrete implementation you tested, for the inputs you tested. And all of that might not be what you eventually have. Also, that's back to the university lecture and the university course. This is not really universal truths. If you run it on your laptop and you get one result and your colleague runs it on their laptop and gets a different result, it's not ideal. And also, this doesn't sound like you can predict very well. So what we'll instead try is do mathematical analysis where we have provable statements, but they hold in a certain abstract model, and we'll come to that. That's the main content for this unit. And hopefully from this, we can derive some hypotheses, which we can then test in an implementation whether they are satisfied. Because often these models make some assumptions. They simplify reality to a certain bit, and you can try to design experiments to test whether those simplifications are justified. As I said many times, the hope is that this is a way to get beyond the current iteration of technology in hardware, software stack, all these things. Things keep changing, and so doing something that's only valid today is not as valuable. What this means is we need precise models for all the things that are involved, namely the machine that things are run on. Already you have lots of machines with you, and they're quite different. Phones usually have an ARM processor, and then laptops have some multi-cores. They have different architecture, different instruction sets, different operating systems, of course, as well. So they vary a bit. We have to bring all that down to a unified model that hopefully captures the main aspects. And we'll also have to model the input data. Remember, algorithms is input to output mappings. And lastly, what are algorithms? That's part of the model as well. Let's start with the easiest, because we'll usually stick to the most basic one here. That's the models for what input data looks like. The traditional ones in algorithm analysis are these three. Either you're pessimistic and you look for the worst possible input for your algorithm, or you're optimistic, you hope for the best, or you're the random guy and you look for the average over some distribution over the inputs. The average performance might be most realistic. It's harder to compute though. Best case performance is a little dangerous unless you can justify that this is to be expected. So in theoretical computer science, people study mostly worst case assumptions. And the simple reason is if you can prove that your algorithm is good in the worst case, you're fine, because that's the worst that can happen. It sometimes leads to overly pessimistic predictions. So sometimes you want to go away from that. But in a way, think of worst case as our default. And if we have reason to believe that this is unrealistic, that this is overly pessimistic, we'll try something else. We'll see a few examples of each of this. Now, if you think about algorithms, they're supposed to solve a whole class of instances of a problem. And usually these instances have a natural notion of size. If you think about a sorting algorithm, it's clear that if you make the list much, much longer, it's kind of obvious it has to take longer to sort it. Whereas if the list is 10 elements, you can probably do it manually. So there needs to be some way of saying the analysis takes this into account. It can't make sense to say, oh, the algorithm always takes X seconds. That's a lie almost surely, because if the input grows, the algorithm will take more time just to read the input. So what we'll do is assume some notion of input size, and we'll always call that n, pretty much always. So little n is a measure for the size of the input. And part of the data model is that you have to specify what the input size is, but is usually quite clear. So for For arrays, it's the number of elements is a natural thing. For strings, the length of the string can be natural. For, I don't know, for a matrix, it could be the total number of entries. For a graph, it could be the number of vertices or the number of edges. It's usually quite clear what makes a reasonable estimate for the size. And then we'll apply each of these data models for inputs of a fixed size. So we fix the size, and then we take the worst possible input for all of inputs of that size. That's the standard model. What this means is all the statements we're making, how fast is an algorithm, you can't really say fast or slow. You have to have a function that depends on the input size. And most algorithms will get slower as the input gets bigger. So the question is, how much do they get slower as the input gets bigger? That's why we'll study asymptotics at the end of this unit.